the new topic here is vector fields, right? Okay, so before I get into what a vector field is, right, let's just recall the use of vectors, say in some simple physical cases, all right? Okay, so this over here, right, what this is representing is that I have a particle actually on a string over here, and the particle is oscillating, well, actually, yes, oscillating around a point, right? So this is, you want to consider this as a vertical plane here, right? And basically what you're doing is you're spinning this particle and it's just rotating uh, in a vertical circle, right? It has enough speed that when it reaches to the top over here, it doesn't collapse and fall down, right? So pretty much you're spinning this with uh, it has a lot of kinetic energy, right? Anyway, so the point here is that, okay, so when your particle is moving in this arc over here at different points, it has forces acting on it, right? It has this tension, and it has the weight due to gravity and so on, right? But what I care about is this blue arrow over here, which is the velocity, right? Okay, so at this point over here, right, in its motion, right, your particle has a velocity that's indicated by this direction over here, right? And the length of this vector is an indication of the speed of the particle, right? Okay, so for example, if you move along, and you notice over here, well, I didn't stop it in time, right? But if I had stopped it right there, the velocity would have been horizontal, right? Here it's because I just didn't stop it right at the bottom, right? The velocity is probably a little, it's pointing a little bit upward over here, right? Okay, what do you want to notice? Okay, and in this case, well, the magnitude of a velocity, right? In other words, the speed, right? The speed is not changing. Um, Speed is not changing because this is apparently rotating with constant angular velocity, right? Anyway, the main thing that I want you to get out of this, right, is at different points over here, your velocity is going to change, right? Okay, so as your particle moves, the velocity vector is changing because, well, the direction of the velocity is changing here, right? So one more time, if you get say right to the top, right, your velocity would be uh, basically horizontal, right? If you right, so let's consider the next case a little more complicated and closer to what we would be looking at in the class, right? Okay, so next application of using vectors, right? Okay, so what we want to do is we're looking at say three-dimensional space, right? So we should know by now that this black plane over here is supposed to represent the XY plane, right? And what I want to start off with is I want to start off considering, say, as a physical example, I'm going to have fluid flow in this XY plane, right? So the example that I'm going to look at, right, is that the fluid is actually going to be circulating around this origin over here, but in the XY plane, right? So it's a moving around like this over here, right? In this particular example that I'm going to look at in a second, right, you have no sort of flow in the vertical direction, right? Everything is happening in the XY plane. Okay, so this example here, right, what this is, what you're going to see in a second is that this diagram is going to illustrate flow, right? Flow around a circle. If you notice that the arrows are pointing and the arrows are sort of moving around this origin over here like this, right? Okay, so that this here, how this is drawn, this is, I guess, what you all did your graphics and so on. This is a plan view, right? So this is what you would see if you look down this way, right, onto the XY plane, right? So this is supposed to be a picture of the XY plane over here, right? So you want to imagine this is flat over here, right? Flat like the xy plane here, right? Okay, so this xy plane here, which is flat, right? Well, let's what this is supposed to be representing here, right? Is this supposed to be representing fluid flow that's circulating around the region, right? Okay, right. So here, this graphic here, what these points are is you could imagine that you have points over here, and these are little, say, like small little particles in your fluid, right? And what's happening is that the particles in the fluid are actually moving with the fluid itself, right? And in this case over here, it's spinning around your origin, right? Okay, so a nice simple way to probably look at this is, for example, if you have, say, like a sink or something like that, with your hole in the middle, right? Well, in the fluid, your water, whatever, is flowing and it's going to circulate and go down the hole, right? It's not, this diagram is not exactly that because you're not seeing the spiral and so towards the origin, but it's sort of close to that, right? So that's one way to look at it, right? You have flow in a sink and stuff, and it's spinning around, and eventually it's going to head down towards the origin, right? Um, okay, if you're looking at the flow in the sink, right? The velocity is actually further out from the hole, right? But as you get closer towards the hole, the water will start to circulate faster, right? So you see that happening over here, right? Okay, so the point over here is that each point, right? So this is supposed to represent fluid flow, right? So you have fluid flow over here, and the arrows such as this vector here, right? What it's doing is, or say this vector over here, right? This point, right? This tail of your vector is indicating at this point your fluid has velocity, right? That is pointing in this direction over here, right? It has velocity that's pointing in this direction, and this is actually the length of this vector is a representation of the speed of the fluid at this point over here, right? Okay, so for example, over here, right, at this point, right, the the fluid is moving vertically, right, and this is an indication of the speed over here, but the direction is vertical, right? So likewise over here at this point, right, your direction is of the fluid flow is vertical, right? The velocity of the fluid flow is vertical. Likewise over here, right, the arrows getting smaller like this means that the speed of the fluid, right, while the velocity is still vertical, right, the speed is actually decreasing, right? Notice this arrow here is bigger than this arrow, and this one is bigger than this one. So the speed is actually decreasing as you move away from the origin, right? And you can see that with the flow of, say, like embedded particles in the fluid, right? Notice over here, yeah, the speed when you're at a distance, a little distance away from the origin, it's slow, and when you're further out, it's even slower, right? Okay, so the point I want to make here is that each point over here, right? So we're not really concerned about the motion of the particles here, right? What we're concerned about is we're concerned about the actual vectors themselves, right? So at each point, right? So for example, at this point over here, you have a vector describing the fluid flow, right? At this point over here, you also have a vector describing the fluid flow, right? Okay, similarly over here, say over here, well, let's use this example, right? This point over here, your velocity is pointing downward, right? So every point in this xy plane, I have a velocity associated to it, right? Okay, and how this particular, okay, so this is an example of a vector field, right? A vector field means that you're looking at the xy plane, and at each point you have a vector associated to it, right? And this would be the sort of form of your vector field here, right? Your vector field, well, it's right, the I and the j is supposed to indicate that it's going to be a vector. This is your x component and this is your y component. And notice this involves x and y, right? And this involves x and y, right? So the fact that this involves x and y, right, means that if I have some point over here, right, this is a certain x and a certain y, right? So if you put in, say, like x is equal to 1 and y is equal to 0 into this, right, what you'd get is, say, you'd get 0 over here and you'd actually get 1 over here, right? Okay, but if you put in, say, x is equal to -1, right, and y is equal to 0, what you'd get is you'd get 0 over here and you'd get -1 over here, right? So what's happening is that the vectors that you get depend on the point xy that you're at, right? So a vector field, this over here, this would be how you would specify a vector field. Okay, it will have this sort of formula. It will have an I and a j over here to indicate your x component and your y component. And depending on what this is over here, right, and what this is over here, you'd get different vector fields. Next example of a vector field, right? And remember what I said, that your vectors over here, these are vectors in two-dimensional space, right? So this is vectors that are lying on a horizontal xy plane like this over here, right? Okay, so we're looking at this example here, right? And well, what's happening over here is that all the vectors are just pointing away from the origin, right? If I have, say, this point over here, right? This point over here, and you notice that if I connect this point to the origin with a line, right? The direction of your vector over here is it's what you get by extending as if you went from the origin to this point over here and you kept going, right? So this is an example of what's called a radial vector field, right? If you have any point, right, such as this one over here in your xy plane, right, the direction of the vector at this point, right, you can get by just simply connecting the origin to this point and then just extending out further, right? Okay, so physically how you could interpret this is again with fluid flow, right? But in this case, what you have is you have, say, like a fluid source at this point, right? So it's as if you have a small hole over here, right? And fluid is coming out of the hole and flowing into the plane, right? And as it flows into the plane, it will actually spread, right? And it spreads in a symmetric fashion out of this little small hole over here. So this is an example of what they call a source, right? So this is a source that I'm talking about here, right? Okay, and what happens is that as it just comes out of this source at this point, right? Initially, well, you have a fair amount of fluid coming out, right? So it will be flowing with a relatively large velocity, right? But as it goes further and further out, the same amount of fluid is in fact just spreading out throughout the plane, so your velocity would be getting smaller as you go further from this source, right? And you can see, right, the graphic over here is indicating that if you had these dots, if you had particles located in the fluid, right, this would be how the particles would move over time, right? They would move away from the origin, right? And they start off with a relatively high velocity because your velocity vectors over here are large, right? And then they start to slow down because the velocity vectors are slower as you go further away from the origin. Okay, so one thing you want to note over here is the form of what is given you. So let's take off these particles, right? Okay, so each point in your xy plane you have a vector associated to it, right? So you want a formula that would actually give you each of these vectors, and that is specified by what's called a vector field, right? So this is a vector field. We saw an example of this when we had the circulation about divergence. So this is a second example. This vector field is a different vector field, right? But it has a similar sort of structure. You have an x component, you have a y component, and both of these are functions of x and y, right? And what that means is that if you go to different xy points in the plane, right, what you're gonna get different vectors, right? So over here, you'll get a certain vector, and over here, you'll get a different vector. All right, so these are the two examples that we looked at, right? You have two different vector fields over here. This one is representing it could physical the physical interpretation of this vector field is that you have the fluid is circulating around the origin, and if you want, it's just heading, and it's probably you could kind of conceptualize that you have a hole over here, and then it's a hole in your say it's a sink, right? And then the fluid is flowing into the sink over here, right? Okay, so it's circulating around and it's heading towards, if you want, the sink over here, right? This is a different case. What's happening is you have a source over here, and then the flow is radial out of this source, right? And you see in the movement of the particles over here, right? Movement of the particles in the fluid is different over here than in this case over here, right? But the point that I want to make is that the vector fields are in fact different, right? This actually, I mean, they do look similar, right? And both of these components are fractions, right? So this is a fraction over here and a fraction over here. Both of them are on x squared plus y squared. But the point here is that this is minus y over here, right? And this is x here, right? And this is x over here, and this is y over here, right? So these are in fact different vector fields, right? And for different vector fields, you're going to have a different pattern of vectors in your vector field, right? So for this vector field, the pattern of the vectors is that it's circulating around like this. And for this vector field, the pattern of the vectors is that it's a radial vector field, right? It's coming out of the origin. So let's look at the formal definition of a vector field, right? So a vector field in your Cartesian plane, right? In other words, a plane such as this or this over here, right? Is a function, right? So this is the function over here, right? That assigns a two-dimensional vector, right? To each point xy, right? Okay, so each point, right, such as say this point over here, would have a vector associated to it, right? And this xy point, which is a different point, would have another vector associated to it, right? So the different points have different vectors, potentially different vectors associated to it, right? Right, so your vector field, this would be how you define a vector field, right? You would have an x component here, right? A y component over here. We call some cases we call the x component p of xy, and we call the y component q of xy, right? So this is your definition of a vector field. Notice over here that this vector field is of this form, right? So the capital P is minus y on x squared plus y squared, and the capital Q is x on x squared plus y squared, right? Okay, and a vector field is continuous if each of your component functions is continuous, right? Okay, so this particular vector field is going to be continuous because these are continuous functions, provided that you're not at the origin, right? At the origin, it's not good because you'd be divided by 0. So this vector field would be defined actually everywhere except at the origin over here, right? So we saw some examples of vector fields that are illustrated on some software, right? Let me show you how to actually plot a vector field, right? Just given its definition over here. Right? Now this is a fairly simple vector field. This vector field, big F over here, the x component is x over here and the y component is 0, right? So this vector field is simply xi, right? Okay, and what I want to do is I want to plot the vector field, right? And at each point xy in my plane, I will get a certain vector, right? So for example, I want at say the point 1 0, right? So well, let's look at this point over here, which is 1 1, right? Okay, so your point 1 1 would be over here, right? So that's your point 1 1. Okay, so your point 1 1 is over here, right? So we want to draw a vector there, right? Okay, so what's the vector at the point 1 1, right? At the point 1 1, when we work it out, we put x is equal to 1, y is equal to 1 into this. You get x is equal to 1 over here, right? And y is equal to 0, right? So I'm simply going to get I plus 0j, which is I, right? And that's a horizontal vector, right? Okay, so that's what your vector would look like at the point 1, 1. It's going to be a horizontal vector like this, right? I didn't draw it exactly to scale because I'm going to draw a couple more, right? So it's going to be a horizontal vector, right? Like this over here, right? So that's at the point 1, 1, right? What about at the point 1, 2, right? So at the point x is equal to 1, y is equal to 2, right? I'm going to have a next vector, right? Now, how do I work out what that vector is? Well, I put in the x is equal to 1 and the y is equal to 2 into this. And I'm going to get I over here and then 0j over here, right? So I'm just going to get 1 x is equal to 1 times I. So at the point 1, 2, I'm just going to get I again, right? Okay, so let's plot that. Okay, so I get this vector over here. I don't need this labeling over here, right? This u and v, right? So you can ignore that, right? The main thing really is that I have at the point 1, 1, I will have a vector, and at the point 1, 2, I have a vector, right? And I can keep going like that, right? So at the point 1, 0, right, which is over here, right? I put in x is equal to 1, y is equal to 0. I work out what the vector is. I'm going to get an I, right? Okay, so I get the same vector actually, right, as in the other two cases, right? So I can plot that. Okay, so that's what I have so far, right? I have these three vectors over here, right, for these 3 points, right? And then similarly at x is equal to 2, 0, right? I can figure out so x is equal, well, let's use 2, 1, right? So at x is equal to 2, 1, which is this point, I can figure out what the vector is at that point over there, right? So I put x is equal to 2, y is equal to 1 into this, and I will get 2i, which is this over here, right? So I plot that. Okay, and notice this vector over here is in the same direction. It's still horizontal, right? But the length is supposed to be twice this length over here, right? And at this point 2, 2, right? I can put x is equal to 2, y is equal to 2 into this, work it out. I'll get a 2i over here. So I get this 2i, and then I plot that as well. And similarly at 2, 0, when I work it out, I'll get 2i, so I can plot that as well. Okay, so you sort of get an idea what's happening over here, right? What's going to happen is that the vectors are always horizontal, but the lengths are going to increase as you move, as the x increases over here, right? If you plot on the side over here, the x in fact is negative, so you'd have horizontal vectors, but it'll be pointing in the opposite direction, right? I draw this vector field using, say, computer software, right? Okay, so the x component is x over here, your y component is 0 over here. When you plot it, you get, notice the vectors over here are horizontal, right? Okay, so you have horizontal vectors, right? And the lengths are increasing as the x values increase, right? If you're on this side, the x would be negative, so the vectors will point in the opposite direction, right? So this, if you compare this to what I had, right? It's the same picture, right? So if this was completed, and so you would, if you completed this diagram and you plotted more points, well then you would get what the software is giving you over here, right? So the point that I want to make is that you can get, if you have a vector field specified like this, right? How you'd actually get an idea. If you wanted to get an idea what the vector field is, you could just simply take your xy coordinates, put it into your function, so you'd have something involving x and y over here, something involving x and y, substitute it in, right? You'd get a vector over there, and then you plot your vector, right? So for example, at the point 1, 1, I get the vector I, and you plot that vector, right? And for the various point, you plot each of the vectors, and that will give you a sketch of your vector field. Alright, so far what we did is we looked at vector fields in the plane, right? Such as this one over here, right? Okay, here the p is minus y x squared minus y on x squared plus y squared, and the q is x on x squared plus y squared, right? So by p and q I mean this over here, right? So this is a vector field in the plane, right? Now what we want to do is we want to consider a vector field in three-dimensional space, right? Okay, so yeah, the general formula for a vector field in three-dimensional space is similar to what it is for a vector field in two-dimensional space, right, in the plane, right? So for vector field in two-dimensional space, at each point xy, right, you're specifying a vector with I and j components, right? For vector field in three-dimensional space, now each point in three-dimensional space, which is specified by x, y, and z, right? What you're going to do is you're going to specify a three-dimensional vector, right? That is a vector with a x component, with a y component, and a z component, right? Okay, so let's consider some examples of a vector field in three-dimensional space, right? So I need to have an x component, a y component, and a z component, right? So these are two different vector fields. I should use a different letter. Okay, so this is vector field big F, and this is vector field big G, right? Okay, so this one over here, x component is 0, right? The y component is 1, right? And the z component is 0, right? So the big P is 0, the big P is 0, the big Q is 1, and the big R is 0 here, right? Okay, so this is a pretty simple vector field. This is actually a constant vector field, right? This one here is also a vector field in three-dimensional space. The big P in this case is minus y, so x component is minus y. The y component is equal to x, and then the z component is 0, right? Okay, so both of these are examples of this general form of a vector field of in three-dimensional space, right? Okay, so what we want to do is we want to plot these, right? Okay, so we'll use some software to plot it, right? So let's start with the first one, which is the F. Okay, and you see in that this vector field, right? Okay, so it's in three-dimensional space, right? So at each point in three-dimensional space, you're going to have a vector associated to it, right? And the vector is a constant vector, right? This is your x direction. This is your y direction, and this is z direction in three-dimensional space. This vector field is a constant vector, right? It's just a constant vector field. You have no x component, you have no y component. This is just only pointing in the y direction, right? And when we plot it, this would be what you'd get, right? So this would be what your vectors would look like, right? Okay, so notice all your vectors over here are just really just heading in this y direction, right? And if you look at a top view of this, you're seeing that the vectors are just all constant vectors, same length, right? And all going in this y direction, right? So this green arrow over here, this green line over here indicates your y-axis, right? So all your vectors are in the direction of your y-axis, right? So the software is good. You should rotate around in three-dimensional space and see what's going on, right? Okay, so that is the big F, right? Now let's look at the vector field, big G, right? Okay, so what this one is this one is, if you look at the top view, right, you look at from the z-axis down onto the xy plane. In other words, if you look at a plan view, so this is three-dimensional space. This is the x-axis, y-axis, z-axis. And if I look from the top, right, you notice that really your vectors here are rotating around your z-axis here, right? So this is rotating around your z-axis. Hopefully this. Right. Okay, so you see in the vectors here and the vectors, this particular vector field in three-dimensional space. At each point in three-dimensional space, for example, at this point you have a vector associated to it, right? And at this point over here, you have a different vector at that point, right? And this vector, if you want, you could think of it as representing fluid flow in three-dimensional space. And this fluid flow is circulating around your z-axis, right? It's circulating around this blue z-axis here, right? The F, right? The big F, right? That we just looked at, right? Right. This one that we just looked at before. This is constant vectors in the y direction, right? And if you want to think of this as fluid flow, right, you could think of this as fluid flowing in three-dimensional space, but it's just a constant fluid flow in three-dimensional space, right, where it's just flowing in your y direction. All right, okay, so let me just zoom in case you didn't see it well previously. Right, so this is the constant vector field, right? Your vectors here. This is the first vector field, and where your vectors are just in the y direction, right? And as I said, you could just think of this as fluid flow in three-dimensional space, where your fluid is just moving in the y direction, right? So in the direction of this green line here, right? Okay. Right, and in the case of the G, right? So you have the second vector field. The vectors rotating around your z-axis, right? Okay, so if you look from the top, you see the rotation around the z-axis, right? And at each point in your three-dimensional space, you have a vector associated to it. All right, so now what we want to look at is, given a vector field, we want to consider what the divergence of a vector field is, and then later on we'll look at what the curl of a vector field is, right? Okay, so I have a vector field in the plane, right? Which means it has this x component here, which is capital P, and this y component here, which is capital Q, right? And how I get the divergence of a vector field, right, is I take this p, capital P, differentiated with respect to x, take the capital Q and differentiate with respect to y, and then I add over here, right? Now what you want to notice is that this divergence here is, it has no I and j components and so on, or I and j vectors, right? This is simply a function, right? So for your vector field, at each point in space, you're going to have some numerical value, right? That is the divergence. Okay, so let's see an example of calculating divergence, right? So I have this vector field, big F here, which is 3i, right? And I want to calculate the divergence, right? Okay, so my formula for divergence is del P del X, del Q del Y, where the P is X component and the Q is Y component, right? In this case, the X component is 3, and then the Y component, Q, is 0, right? Okay, so to get divergence, you differentiate the 3 with respect to X. Differentiate is 0. And this is wrong here, right? So this should be derivative with respect to y over here. And this should be derivative with respect to y here, right? Okay, so differentiate with respect to x here and differentiate with respect to y over here. And what I'll get is, I'll get a 0 here, right? Okay, so the divergence of this constant vector field is 0. And now let's consider this one here, this 3x squared I, right? This vector field 3x squared I. So again, I want to differentiate the p with respect to x. This should be, again, derivative with respect to y. This should be derivative with respect to y, but it doesn't affect the answer, right? Okay, so differentiate the 3x squared with respect to x. I get 6x over here, and then the q is 0. So when I differentiate the q with respect to y, I'll get 0 here. So the divergence of the vector field big G here, right, is 6x, right? So in this case, this is non-zero, right? Right. Okay, so what we want now is we want to get an interpretation of what this divergence is, right? Okay, so right, what we're doing is we will use, so we'll start with this example over here, this vector field F here, right? So the vector field is this vector field here, constant vector field. And we want to regard that as we're going to have flow, right? So this is a sketch of your vector field. The arrows over here would be your vector field. Okay, so arrows over here would be your vector field, right? And you could regard this as you have fluid flowing in the plane, in the xy plane, a horizontal xy plane. And these vectors are telling you what the velocity is at each point for your fluid flow, right? Right. Okay, right. So what we want to do is we want to get an interpretation of these functions that we calculated over here, right? So what we do is we're looking at a point xy, so we're interested in the divergence at a specific point xy, right? And what you do is you consider a small box with length delta x and height delta y, right, at this point, right? Okay, so what you do now is you in order to get your interpretation of divergence, which let's just, again, we're considering this vector field big F to start off with, right? So to get our interpretation of divergence, what we do is we consider in this vector field as velocity of some fluid flow, right? So the fluid is flowing in a horizontal direction. Notice the speed is not increasing. Okay, so it's your fluid is flowing in this horizontal direction, in the direction of the x-axis, right? Your speed of the fluid is not increasing as you move in the x direction. Matter of fact, it's just constant everywhere, right? Okay, so how we want to interpret divergence, right? Divergence at this point is the net flow out of this box over here per unit area, right? Okay, so what do I mean by net flow, right? There's these arrows over here are pointing in, right? So you want to regard at this side over here, on this side of your rectangle, you're going to have flow into your box here, right? And on this side of your rectangle, you have the flow out of this side, right? So you have flow in on this side, and then you have flow out on this side, right? And what you want is net flow, right? You want is net flow out of this box over here, right? Now, net flow is equal to flow out minus flow in, right? So what's your flow out, right? Your flow out is from, you have flow out on this vertical side over here, right? And you have flow in on this vertical side over here, right? And because the length of this side is the same as the length of this side, right? And because the velocity of the fluid flow is the same on this side as it is on this side, right? The flow out over here is equal to the flow in over here, right? So when you subtract them, you get 0, right? All right, and then also, well, what's happening on these horizontal sides, right? Well, what's happening on these horizontal sides is that the fluid is just flowing along the horizontal side, right? Because the, the velocity of the fluid flow is just horizontal itself, right? So as we want is just getting along these horizontal sides, so nothing is cutting across, right? The only time you cut across is on this vertical side over here, in which case you have flow in, right? And on this side over here, where you have this vertical side where you have flow out, right? Your net flow over here is the flow out minus the flow in, and you have no flow. The flow is 0. Flow through these two horizontal sides is 0. So your net flow is flow out minus flow in. And because the flow out is equal to the flow in magnitude, right, you're just going to end up getting 0, right? So overall, the fluid, how you could read this also is the fluid going in, right, is equal to the fluid going out, right? Nothing is accumulating, right, in this box over here, right? So that's the interpretation of divergence, right? Divergence is interpreted as net flow out of a small box located at the point that you're interested in, right? Per unit area, right? Okay, and then we calculated for this vector field big F, which is 3i, your divergence is equal to 0, right? So what that means is for a constant vector field, if you draw any, say it's like a small box at a point that you're interested in, which is xy, right? You're not going to have any flow accumulating in that box, right? The flow out is going to be equal to the flow in. Alright, okay, so now what I want to do is I want to interpret the divergence of this vector field, right? So this vector field, big G, when I work out the divergence of it, it turns out to be 6x here, right? Okay, so this is non-zero in this case, right? So I want to understand why this is non-zero, at least get some sort of physical idea, right? Okay, so we're looking at the vector field 3x squared I, right? So you want to notice that this vector field is in fact horizontal, right? You have no y component, so the vector field would just be horizontal, right? And this is in fact a plot of that vector field 3x squared I, right? Okay, so it's a horizontal vector field. So this is your vector field 3x squared, right? I with no j component, right? Okay, so the vector field is just horizontal over here, right? what you want to notice is that when the x increases, right? So for example, this is x is equal to 1. If I have x is equal to 1 over here, I'll get a vector of length 3, right? Which is represented by this, right? If I put x is equal to 2 into this, I'm going to get a vector 3 times 4, which is 12, right? So you see that this vector at x is equal to 2 and the x is equal to 2, the vectors are longer, right? So then likewise at x is equal to 3, the vectors are going to get even longer, right? So what's happening with this vector field is that it's a horizontal vector field, but the lengths of the vectors increase as you move in the x direction. All right. Okay, so now that we get that what the vector field of the big G looks like, right? Let's see if we could understand what the divergence is, right? Okay, so again, what we're doing is we're looking at a specific point xy over here, right? And we're considering a small box located at that point xy, right? And what I want to do is I want to consider the net flow out of this box over here, right? Okay, so again, also I have no flow cutting across the horizontal sides over here, right? The only flow I have is through the vertical sides, right? But in this case, what's happening is that the the fluid flow is increasing, the speed of the fluid flow is increasing as you move in this x direction, right? So what you have is you have uh, that you have more flow out on this vertical side than you have flow in over here, right? So what that means is using this idea of what a net flow is, right? Your net flow is flow out minus flow in, right? So in this case, the flow out is larger than the flow in, right? So what I'd expect is I'd expect that I have positive net flow for this over here, right? Okay, and you see that the divergence is equal to 6x, right? So on this side of my y-axis where the x is positive, right? What's going to happen is, well, when x is bigger than 0, right? I'm going to get something that is positive over here, right? So for example, if x is equal to 1, I'll get 6, right? Okay, so somewhere over here where the x is equal to 1, what that means is, well, I should say it like at this point over here, right? So at this point over here where the x is equal to 1, right? What's happening is that the net flow out of a small box over there is positive, right? So somehow you have more fluid flowing out than you have flowing in, right? Which is probably not physically realistic, but well, we're not really. This vector field isn't necessarily representing probably like a normal fluid flow, right? But just as a vector field as an abstract vector field, when we calculate it, right? What it means is you're going to have net flow out over here, right? Because the divergence is 6x. Right, so now what we want to do is we want to look at divergence of a vector field, right? But now a vector field in three-dimensional space. So you want to recall that a vector field in three-dimensional space, what that means is that at each point x, y, z in three-dimensional space, you're going to have a three-dimensional vector. In other words, a vector with x, y, and z components. And those vectors can change from point to point in three-dimensional space. Right, so, well, what's the divergence of a vector field in three-dimensional space, right? So let's just recall what the formula is for the divergence of a vector field in two-dimensional space, right? So to get the divergence for a vector field in two-dimensional space, what you do is you take this, the x component, which is big P, and you differentiate with respect to x. You take the y component, which is big Q, and you differentiate that with respect to y, and then you add them, right? Okay, so your divergence for vector field in three-dimensional space, what you're doing is you do something similar, right? You take your x component, differentiate that with respect to x. Take your y component, differentiate with respect to y, and now you take a z component, differentiate with respect to z, and you add it, right? Okay, so this is your definition of a divergence of a vector field, of a three-dimensional vector field, right? And if you compare it to the expression for divergence of a two-dimensional vector field. You see, it's essentially the same thing, except over here, well, now you just have an extra term for your z component. All right. Okay, so what I want to do here is let's look at an alternative way of expressing divergence of f, right? And what you're going to do is you're going to use this operator here, this vector differential operator, which is called del, right? Or it's also called nabla, right? If you're more into differential geometry, right? But in this course, we call it del, right? So what this is saying, this definition is saying, is that the divergence of f I can write alternatively as del dot f, right? And this sort of notation over here, where you have vector expressions involving this del operator, right? This is something you will see in some of your other courses, especially if you're mechanical, right? Or chemical, right? Well, also electrical too in your field theory, right? Okay, so right, so you have divergence of f is del dot f, right? And what we want to do is we want to understand this, right? Okay, so I'm saying that this del is a vector differential operator, right? Okay, so what is an operator, right? Well, let's just look at this over here, right? So consider this, right? I think everybody knows what this means. What this means is that you have x squared over here, and what you need to do is you want to do something to it, right? Which is the x squared you want to differentiate with respect to x, right? When you differentiate the x squared with respect to x, you get the answer that you would expect, which is 2x, right? Okay, right, so what this ddx just by itself, right? This expression over here, right? What this is an example of an operator, right? So this operator here is acting on x squared, and when it acts on x squared, you get 2x over here, right? Okay, so ddx here, your normal ddx that you know from before, right? This is an example of an operator, and it's a differential operator because, well, you're using it to differentiate, right? So likewise over here, this is a differential operator, right? So it's an operator, so it's going to be acting on something, right? And in this case, what it's acting on, it's acting on this vector field, right? F, big F, right? Okay, it's a differential operator because how it acts is, in a sense, similar to this differentiation over here, right? Okay, so what you have is your vector field has x, y, and z components, right? And what you're going to do is when this operator acts on the big F, right? Essentially, what it's doing is going to differentiate each of the components with respect to x. With respect to x, differentiate the y component with respect to y and the z component with respect to z, right? Okay, so is an operator. It's gonna act on your vector field. So this del as an operator is gonna act on your vector field. It's a differential operator because you're going to be doing some differentiation over here. And the last thing you want to realize is that it's a vector differential operator, right? Okay, so this here is in this is, if you write it out, it will have vector form. Okay, so this expression here, which ddx I and the ddxy and the dyj and the ddzk, right? This is, I mean, I can write a vector like this, or alternatively, I can write it in this sort of component form, right? Or sorry, this column vector form, right? Okay, so you have a partial here with respect to x, you have a partial with respect to y, and a partial with respect to z, right? Okay. Right, so what you're gonna do over here is I'm saying that the divergence of f, right, which is this definition over here, right, I can get it by using this vector differential operator, right? So if I take this vector differential operator, right, okay, so for the time being, just think of this as a vector over here, right, and think of the vector field as just a vector over here, right? And what you want to do is you're going to take dot product here, right? So dot product in the normal sense, right? Well, uh, not quite in the normal sense, but you're going to be taking a dot product over here, right? So I have this vector with x, y, and z components, right? So if you want, you have it in column form like this, and then similarly you have this vector field with x, y, and z components, right? Now, when you're working out a dot product, well, how do you work it out, right? What you do is you take your x component over here and you multiply it against this x component here, right? Now, so that's, you get the ddx times the p, right? So I have the ddx times the p. And what you want to do is you want to interpret this correctly, right? This is not quite, say, like normal multiplication. What this means is you're going to take the ddx over here and you're going to act on the p over here, right? So in other words, while it looks as if well, in a sense, symbolically, what you're doing is you're multiplying your operator here against the function p, right? But really, you want to read this as what you're going to do is you're going to take this p over here and differentiate it with respect to x to get this, right? And similarly, when you're working out your dot product, it'll be your y component over here multiplied by this y component here, right? And that gives me this. And how you want to read this is differentiating the q with respect to y, right? And similarly, when you consider the z components, you get dz times r, which really means you want to differentiate the r with respect to z, so you get this, right? And now, when you look at this over here, right, this expression is exactly the same as what the definition of divergence is, right? So that gives you that del dot f is equal to divergence of f. Alright, so let's use the vector differential operator that we just looked at, right? So your del over here, right, to define something called curl, right? And what curl does is, well, I mean, you use it for certain things, right? You'd use it, for example, in say like Stokes theorem and so on, right? But right, so your curl, we want to be able to calculate curl of a vector field, right? Okay, so we're looking at curl. For us, we will look at curl just in the three-dimensional case, right? You can define curl for the two-dimensional space as well, right? For a two-dimensional vector field, right? But we only really will look at it in the three-dimensional case, right? Okay, so I have a vector field, right? A three-dimensional vector field with your x, y, and z components, right? The p, q, and r, right? Okay, so how are we going to define curl of a vector field, right? So curl of the big F, right? And the notation, okay, so curl of the F, and how we define it is using the del operator, the vector differential operator that we just talked about. And we're going to take the cross product with this vector field F, and we want to interpret this cross product in a appropriate way, right? Okay, so anyway, so well, how do you take a cross product, right? If you regard in this del as just a vector, right? So the del is ddx, ddy, and ddz, right? Okay, so the del is ddx I component, ddy j component, and ddz k component, right? So your first vector over here, you're taking your cross product of vectors, right? You're doing this in a sense. Well, to start off with, your notation is the standard way, right? When you take a cross product of two vectors, you take your row over. You take first vector, write it as your second row, and you take your second vector over here and write it as the third row, and then you have the I, j, and k over here in the first row, right? Okay, so your first vector is the del here, and the del is this ddx, ddy, ddz, right? So I have that in the first row. Okay, and f is this vector, if you want, with p, q, and r, so that goes in my second row, right? Okay, and now what you're doing is you're working out cross product, right? And how you work out, well, cross product, you're doing this in a way normal, in a sense you're doing it in a normal way that you evaluate cross product. You're gonna multiply this against r. Okay, so you multiply this, if you want to get the I component, right? You multiply the d dy against the r, and then you multiply the d dz against the q, right? And you subtract, right? Okay, so the d dy against the r is dr dy, right? So you want to interpret the multiplication of the d dy against the r as a derivative of r with respect to y, right? And you want to interpret the multiplication of the d dz against the q as the derivative of q with respect to z, right? Okay, so you differentiate here the d dy against the r, and then the d dz against the q, and you subtract, right? Okay, so that's similar to what you do for normal cross products, right? And then it will be minus j times d dx against the r by the d dz against the p, right? Okay, so it's minus d dxr minus dp dz, right? When you could actually multiply throughout with the minus sign, and you'd get what I have over here, right? Okay, and then finally, to get the k component, it's d dx against the q minus the d dy against the p, right? So dp dy. So this is a definition of curl, right? Now, if you want, you can actually define curl just by using this, right? But you see, this is not really the easiest thing to remember, right? And it's much easier to probably just remember the shorthand notation over here, right? So this is one point about this your vector differential operator, the del over here, is that you could define, say, both the divergence and the curl in a shorthand way using your vector differential operator, right? So that's probably one of the main reasons that you want to use it, right? Okay, right, so let's do a calculation of this, right? There's a calculation here in the notes. You can take a look at this, right? But I'm gonna do a somewhat simpler vector field, right? Because I want to sketch this one, and I want to give you an interpretation of curl, right? Okay, so this vector field f is the x component, the big P is minus y, the big Q is x over here, and the r over here is 0, right? You have no k component, right? So the r is equal to 0. You see that 0 there, right? Okay, so I want to work out curl of this, right? So curl of this, well, the second row would be a vector differential operator. The last row would be the minus yi and the xj, right? So this over here. And what you do is now you take an you work it out, right? You work out so anyway, so curl cross f, right, is, in order to do it, you need to work out this determinant. So it's as was defined over here. You're going to differentiate the 0 with respect to y, and differentiate the x with respect to z, and you subtract, right? Now when you differentiate 0 with respect to y, you're just going to get 0. And when you differentiate the x with respect to z, again you're going to get 0, so you're going to get 0 minus 0 over here, right? Which is just 0, right? So you have no I component. And then, alright, okay, so for the j component here, what you do is you differentiate the 0 with respect to x, right? And you'll get this 0 over here. And you differentiate the minus y with respect to z, you get a 0 over here, and then you get 0 minus 0, right? So your j component is equal to 0, right? And finally, to get the k component, what you do is we're going to differentiate, to get the k component, differentiate the x with respect to x, and that gives me 1. And then differentiate the minus y with respect to y, and that gives me minus 1, right? So I have minus minus 1, and that gives me 2k, right? So the curl of this vector field is in fact a constant vector field here, right? So how you want to read this is that this 2k is, this curl of f is a vector field, right? So at each point in three-dimensional space, what you're going to have is you're going to have a vector, right? And that vector is 2k, right? So that is curl F is a vector field where at each point the vector is 2k, right? So we want to consider interpretation of curl of a vector field, right? So we're looking at this vector field here, this minus yi+xj, right? And this over here, this is a sketch. Okay, so remember this is a vector field in three-dimensional space. Here I have three-dimensional space here, right? And what we have here is that the vectors are rotating around the z-axis. So we in fact saw, okay, so this is the same vector field. The x component is minus y, the y component is x, and the z component is 0, right? And we saw this vector field already, right? What this vector field does for you, it's rotating, it's swirling around your z-axis, right? It's rotating around your z-axis, right? And this here is a plan view, right? If you look from the x-axis and you look down, right, this would be what you'd see. You'd see the xy plane, and you see that the vectors are rotating around the origin here, right, or the z-axis. Okay. Okay, so what's our interpretation of curl, right? Well, curl, what it does is, curl is, in a sense, is at a single point, it is measuring rotation of the vector field, right? So what you want to do is you want to imagine, for example, that you have, say, this a small ball, right, located at a specific point, right? And the ball can actually, it's as if the ball is punctured uh, through and through with an axis, right? So this green this little green arrow over here is meant to indicate an axis, and your ball over here is spinning around the axis, right? So your ball has a certain amount of, if you want, the ball would probably have, say, some sort of friction so that the fluid flowing around it would be able to catch it and, say, rotate it and so, right? Okay, so what it would be curl, right? How do you interpret curl, right? Well, this ball over here, right, is rotating with a certain amount of angular velocity, right? At any given point, it will be rotating at constant angular velocity, and that constant angular velocity, this constant angular velocity is proportional to the magnitude of the curl vector, right? So remember, your curl vector, we worked it out to be 2k, right? So your curl vector is 2k, right? So for this particular example here, your the angular velocity is proportional to curl. Matter of fact, it's a half the magnitude of the curl, right? Okay, so the curl vector is worked out to be 2k, right? So what we got was 2k over here, right? Okay, which is the same thing that is stated over here in this example. This is 002, so this is 2k here. So the angular velocity is in fact half the magnitude of curl, right? And half the magnitude of this vector, sorry, the magnitude of this vector is 2, right? So half of the magnitude of the vector is 1, right? So your angular velocity, right, that this little ball is rotating around with is 1, right? Okay, so curl is a vector, right? So at any point in the associated vector field that you're taking the curl from, right? What curl is doing is curl is measuring rotation locally, right? Okay, so as I say, what you do is you consider just say a small ball, right, that is rotating around an axis, and the magnitude of the angular velocity for that rotation is equal to half the magnitude of curl, right? Now, what about the direction of curl, right? Now, if you align this axis in, this is where, notice the alignment of this axis is actually in the vertical direction, which is the same as the direction of curl over here, right? Which is in the k direction, right? Okay, so the curl vector, right, has the magnitude, which is indication of the angular velocity of the equal to the angular velocity of uh, the rotation of the ball about the axis. But then the axis itself, right, this axis over here, the direction of this axis is coming from curl over here, right? And the point is this direction, which is k, right, would give you maximum angular velocity, right? If in fact you took this axis and you consider the ball rotating about an axis that was probably pointing in the y direction over here, right? You actually wouldn't get any rotation, right? Okay, so the rotation would change according to how you align the axis over here, this ball, right? So again, you're thinking of this ball as being spinning around this vertical axis over here, right? Okay, and so spinning around your vertical axis here, right? And what you could do is you could potentially move the axis itself, right? And if you move the axis, right, and then you consider the rotation, right, what will happen is that you may have less rotation, right? And what I'm saying in this particular example, if I take this axis and I line it up with, say, the y-axis here, right, I will in fact get no rotation of this ball, right? Okay, right. So that is a basic interpretation of what curl is, right? Curl is, and it's curl at any point, right? So if you consider, say, some other point over here, you would also have a similar rotation, right? This particular the curl over here is constant, right? So matter of fact, that's because of what this vector field is, right? So if you move to any point uh, in this three-dimensional space, right, what's going to happen is you'd always have the same sort of rotation, provided the axis is pointing vertically, right, in the k direction. If we wanted, say, a second example of what your curl vector field will look like, right? Let's consider this vector field, right? Where your x component is x, your y component is xy now, right? And then the z component is 0, right? Okay, so for this vector field, you have no component in the z direction, right? So all the interesting stuff is just happening in the xy plane or planes parallel to the xy plane, right? So what that means is that if you look at a plan view of your vector field, right? Really, you're getting an idea of what's going on, right? Okay, so you see over here that if you move to different points, right? So for example, over here, right? The fact that you have no z component means that when you work this out, right? This is gonna happen, right? You're gonna have 0 here and 0 here, right? Okay, so if I move and I look at the curl in different locations, right? So for example, over here, right? I have no curl, right? You have no sort of rotation at this origin, right? But if I move now and I move, say, like over here, right? What you want to notice is that the curl over here is positive, right? Because you have some sort of rotation over here at this point, right? So your curl will change depending on where you are in your three-dimensional space, right? This over here, I mean, I'm just looking at a plan view of the three-dimensional vector field so that things would be less confusing, right? But what you do is you could think about it this way, right? So if you look at what's happening in the three-dimensional space, this diagram is sort of unfortunate because you have too many arrows in it, right? But if, for example, like you look over here, right, and you consider, this is what I was talking about over there, what you're going to have is you're going to have more rotation, right? So again, if you look at your plan view, over there you have more rotation versus, say, uh, over here, right? Well, if for example you're around there, right? You don't have any, according to the calculations, you don't have any rotation over there, right? It's zero, right?